Good evening, everybody. I'm Fred Passman. I'm the commander of the Continental Commandery of the Naval Order of the United States. And I want to welcome everyone to this evening's uh, Naval History virtual lecture. Uh, Before I introduce tonight's guest speaker, I just want to remind everybody that the Naval Order is the oldest um, organization with the United States where all of our members have a heritage to the maritime services. And our mission is to preserve, promote, celebrate, and enjoy our nation's maritime history and heritage. For more information about the Naval Order, I invite you to visit the Naval Order website, which Mark will show on the bottom of the screen in just a second. Um, Also, I want to take this opportunity. It's not too late to participate in this year's National Congress, which will take place from 18 to 22 August in beautiful Alexandria, Virginia, just across the river from Washington, D.C. For more information about that, visit the Naval Order website and click on the links to the 2022 National Congress. With that, I want to turn our attention to this evening's guest speaker, Dr. Frank Blazich. Uh, Frank is the Curator of Military History, Division of Political and Military History at the National Museum of American History at the Smithsonian Museum. Uh, Before arriving at Smithsonian, Frank first served as a historian at the U.S. Navy's Seabee Museum in beautiful Port Hueneme, California. Yay. And then moved a couple of miles east to Washington, D.C., where he served as the historian in the History and Archives Division of the Naval History and Heritage Command. Um, he served there until December of 2016, and then he served on a uh, task force netted Navy. We'll have to ask about that during the question and answer session later, working under the Office of the Chief of Naval Operations. 2017, then he assumed his current position at the Smithsonian. Um, Fascinating topic for this evening. So without further ado, Frank, welcome. Delighted to have you back. I do want to mention that Dr. Blazich is back for the second time, and he previously gives a fascinating account of the development and use of lighterage during World War II that really made a tremendous difference on our ability to succeed in our various amphibious operations, bringing troops and equipment ashore quickly and efficiently. So I highly recommend going to our commandery's website, go to past events, and you'll find his August 2020 presentation there. Quite a tale to be told. But tonight, it's all about torpedoes. And Frank, why don't you just take it away?
Great. Well, thank you very much, sir, and good evening, ladies and gentlemen. I'm going to try and share my screen here to bring up my slides. I think I'm doing this correctly. Hold on, let's see. All right, and there we go. So tonight we're going to talk about the development of the Mark VI Mod 1 torpedo exploder, which I kind of refer to as merging evolutionary and revolutionary technology. Now, I should note that when this research project began, the global pandemic limited my access to archival sources. Now, since then, I've been able to obtain some archival sources, but I've also discovered some of the records from the 1920s, which were previously available for researchers, have been apparently reclassified, and I have to do a FOIA request. So I'm not sure when that will be processed, and thus there's quite a bit that still remains to be understood about the development of this piece of technology. Nonetheless, I hope this talk will prove enlightening as my main and most valuable source is actually a surviving exploder, which has been long ignored in the collection of the National Museum of American History. And much of the imagery you're going to see tonight has previously not been seen by modern audiences and really has kind of been rediscovered, if you will. Now, in 1915, American engineer Alan A. Canton claimed to have perfected a self-propelled torpedo guided by magnetism, able to defeat the latest incarnation of the all-powerful warship, the Dreadnought. Canton had reported his torpedo had 100% accuracy and could dive deep to strike the unarmored portion of a warship's hull. Now, the secret of his weapon involved the use of electromagnetism to detect the presence of any great mass of metal to help guide the torpedo to its target. Suffice to say, Canton's torpedo did not materialize, but his interest in harnessing magnetism to an underwater weapon to detect and destroy warships would become reality in the interwar period with the U.S. Navy's Bureau of Ordnance, or BWARD's, development of the Mark VI torpedo exploder. The development of the Mark VI merged this evolutionary knowledge and design of torpedo contact exploders with this revolutionary magnetic influence technology incorporating the latest electromechanical inventions. And the talk tonight is really going to try and detail the origin and development of the Mark VI exploder in the interwar period by examining the physical object itself. Now, beginning with the design, development, and testing of the first self-propelled torpedo by Robert Whitehead in the late 1860s, all torpedoes entering service in World War I detonated their explosive charge via physical contact with the hull of a vessel, and this was an action involving the use of a unique exploder device. The very first American torpedo exploder is found in the Mark I Hal torpedo developed by Captain John A. Hal in the 1880s. Driven by a 132-pound flywheel spun to 10,000 revolutions per minute, Hal's torpedo proved weightless and it had excellent directional stability. Now, this was adopted in 1889, and the Navy ordered 50 of these torpedoes from the Hotchkiss Ordnance Company. In order to detonate the weapon's explosive charge, which consisted of 99 pounds of wet gun cotton, Hal devised what he called a war nose, which screwed into the front of the warhead. And you can see one of these here. This featured a safety mechanism in the form of a small reverse pitch screw fan, and this would render the torpedo safe until it was fired. Once it was launched, the fan would slowly unwind from the body of the torpedo forward until it had completely unthreaded itself about 30 to 40 yards from the point of release. And when the torpedo impacted a hull, a conical point affixed to a central sleeve would be pushed inwards. This would sever a lead shearing pin before compressing a firing spring, which tripped a sear spring to release a central firing pin, which, released from then spring tension, tripped a sear spring to release a central firing pin, which impacted a percussion primer to detonate a booster charge of fulminated mercury primed with dry, long staple gun cotton. And this then, after all of that, would detonate the main warhead. Now, the E.W. Bliss Company also licensed manufactured the 3.55 by 45 centimeter Whitehead Mark I torpedoes for the Navy. And they used what they call War Nose Mark I, and this was similar to the Hal in that it screwed into the front of the warhead. And the War Nose Mark I, seen here, functioned similarly to the Hal. It armed itself after 70 yards of travel, and like the Hal, it would only work on a 90-degree angle, with the warhead and the target aligned on a longitudinal axis. But what about less than textbook torpedo attacks, when you have to take kind of an angled shot, an oblique or glancing impact? Well, Whitehead and E.W. Bliss each developed war noses for these situations. The Whitehead War Nose Mark II weighed 4.5 pounds, and it featured 4 levers, we could call these whiskers, which extended outward from a central screw fan along the cardinal points of the warhead. You can see these here in the upper left in that patent drawing. Now, should the torpedo strike a glancing blow on a target, one of the outward levers would trigger the release of a firing pin and the detonation of the booster charge and then the warhead. Frank M. Leavitt, an engineer of E.W. Bliss, designed and then patented an American war nose for direct and oblique impacts that blended aspects of both the Hal and the Whitehead designs, but added several safety features, and that's actually the patent you're seeing here. The point of the safety features is really to prevent premature detonation or arming of the weapon until it had moved a considerable distance from the firing vessel, and to avoid essentially the torpedo immediately firing and detonating and thus potentially destroying its firing vessel. So in 1908, the Navy decided to actually conduct, with a novel concept, a live fire test of a Whitehead torpedo. And this was really not about the torpedo. It was intended to test developments in watertight bulkheads. So on June 13th, 1908, a Whitehead torpedo, a Mark I, and its 220-pound warhead of wet gun cotton was actually fired along a trolley to impact a precise spot on the hull beneath the armored belt of what you see here, the Monitor, USS Florida. And this test was conducted off Pine Beach near Naval Station Norfolk, with a large party of dignitaries in attendance, which included the Secretary of the Navy, Victor Metcalf. The warhead detonated as designed. It showered Florida and her skeleton crew of 20 with water, as well as the steel torpedo fragments. The bulkheads survived their impact of the test, although the ship did have a 20-foot-long hole in her hull. And the torpedo and its exploder had demonstrated its abilities without cause of concern. As far as everyone was concerned, it worked as designed, even if it was a controlled test and fired along essentially a rail as opposed to free-floating in the water. There was no cause for concern. Everything worked fine. But then, in 1912, several years later, the Navy will decide to work on what becomes the 21-inch Bliss-Leavitt Mark VIII torpedo. This is a much larger torpedo. It has a warhead of originally 321, later 475 pounds of TNT. It could travel at 27 knots at a range of about 10,000 to 15,000 yards. And it was really intended as a long-range anti-surface ship weapon for the Navy's fleet of destroyers, ever-growing fleet of destroyers. Now, accompanying this torpedo is what you see here, the Mark III exploder. Now, this was designed and developed by the Naval Torpedo Station at Newport, Rhode Island. And unlike previous torpedo exploders, it would not fit in the nose of the torpedo, but actually flush into the underside of the warhead, forward of the transverse center line near the center of the long explosive charge. The concept here is, instead of having the explosive behind the exploder, you actually essentially embed the exploder in the bulk of the explosive material. So you have a more rapid detonation and a more effective blast. Now, again, this is changing the orientation of the exploder's firing mechanism from a parallel to a perpendicular orientation in relation to the torpedo's path of travel. The Mark III weighed 5.25 pounds, and it also had a 3-bladed impeller as the foundation for its safety mechanism. So in this case, once the torpedo is fired, rather than putting that impeller at the nose of the warhead, it's now underneath the torpedo. So the water will flow around that torpedo, it'll spin the impeller, this will drive a gear train, which rotates an arming gear, which after 140 yards of travel from the firing point, it will move the detonator carrier out of a safety chamber. And on the left side of the screen there, you should see that cap at the top. That's actually a part of the safety chambers within there. And that will then it'll move up from there. And once it's out of the safety chamber, the detonator charge will actually move into the booster cavity in the warhead. This action, in turn, is also compressing the firing spring and unlocking the trigger mechanism. On the right-hand side of the screen, if you see that spring up at the top, there's a little plate above it, and there's 2 pins, and those are your firing pins. And I'll point down through our schematic. So the Mark III is utilizing Newton's first law of motion, the inertia principle. The impact of this torpedo against the target will shift a large inertia ball, and you can see it there in the lower left. This will displace a smaller ball bearing, which then releases the trigger. This activates a spring, which pushes a firing pin body holding a pair of short firing pins upwards into a percussion primer. This activates 65 grains of fulminated mercury, which will ignite half a grain of gun cotton, and then that triggers the booster charge of 8 ounces of Tetrol, and that will detonate the warhead of TNT. The inertial impact system made the exploders extremely sensitive to contact. A blow of less than 5 pounds of force will actually trigger a detonation. The sensitivity will in turn negate the need for the whiskers and enable operation at any angle of impact. The Mark III also has an anti-circular run and anti-countermining mechanisms for added safety and effectiveness of the torpedo. But the first actual firing of one of these weapons will occur on May 21st, 1917, when the destroyer Erickson, seen here, only a week after arriving overseas with the 7th Destroyer Division, will close on the German submarine U-48 and will fire a Mark 8 torpedo at a range of 7,000 yards, albeit without any effect. By the armistice of 11 November 1918, only 10 additional torpedoes had actually been fired by the U.S. Navy, and these were all against U-boats, none of which found the side of an enemy's hull. So essentially, outside of laboratory testing, the Mark III exploder's performance in combat remains unknown, and much less the combat performance of any American torpedo exploder to date. But interest in harnessing the magnetic influence technology for a torpedo exploder would actually come in response to evolutions in warship design to defend against torpedoes. Now, initially you have torpedo nets, and they will protect existing vessels, and you can see a torpedo net extended here on the left. But newer vessels incorporated additional armor plating and/or expendable hull sections such as torpedo blisters or bulges to absorb the blast of the weapon and maintain the structural integrity of the hull. And for those who've been following the dry docking of USS Texas, you can actually get a good idea there of the torpedo bulges on the side, also seen here on the photograph on the right. So a torpedo that's detonated by impact exploder against these defenses will damage a ship, but it's probably not going to be a singular killing blow, unless your damage control is god-awful, or it manages to have that golden BB effect and hit just the right spot. But this is why magnetic influence is so fascinating. It offers a way to detonate a weapon without direct impact. So thus a single torpedo detonated under the keel of a vessel by magnetic influence could avoid these defenses and potentially destroy a warship. And this is a far more economical use of opportunity, of torpedo mechanism, and explosive than mere impact exploders could then provide. And in fact, in 1924, the Navy detonated a 400-pound charge of TNT 15 feet beneath the hull of the test of the decommissioned battleship South Carolina. This is BB-26. And the results of the test convinced naval planners that it would be impossible to severely cripple or disable a major warship equipped with torpedo blisters unless some way could be found of exploding the warhead directly beneath the hull where there were no protections. So the Bureau of Ordnance saw in a practical magnetic influence exploder a solution to a bigger problem of torpedo supply. Now, as the fleet and demand for torpedoes expanded in World War I, remembering the flush deckers and this massive expansion of destroyers, all with torpedo tubes, the Navy finds itself needing to increase production. We need the weapons to supply these ships, not just for their immediate cruising, but and then combat replenishment needs. But the complicated nature of the entire weapon, from the warhead to the tail section, essentially makes torpedoes very difficult to build. They're very difficult to maintain. The logistics to them is very complicated. In 1908, the Navy will open a factory at the Naval Torpedo Station in Newport on Goat Island. And this is intended to manufacture torpedoes and also really get around the monopoly then held by E.W. Bliss Company. And during World War I, neither Newport nor Bliss could fill all the Navy contracts. This necessitated Buord to break ground on a new torpedo factory in Alexandria, Virginia, which is still there. It's actually has some fantastic art galleries if anyone's ever been there. And in 1923, though, the Alexandria factory will go into mothballs, and all the contracts for Bliss will cease, thus making Goat Island and Naval Torpedo Station Newport the nation's sole designer and supplier of torpedoes. What could ever go wrong with monopoly? So with this potential to develop what I like to call the one-shot, one-kill torpedo in technological reach, or seemingly within technological reach, the Bureau of Ordnance chose to act. On 30 June 1922, Newport launched Project G53 under utmost secrecy to develop an exploder to use a ship's inherent magnetism to attract the torpedo or trigger the warhead's detonation. And the research effort eventually zeroes in on detonation actuated by detecting perturbations in the Earth's magnetic field initiated by the presence of a steel vessel. Now, I have to note, while the knowledge of the Earth's magnetic fields had increased for centuries, Newport's project confronted an unbelievable gap in the knowledge of the perturbations beneath a ship's hull, or ship's keel, as well as a need to compensate for the variation in Earth's magnetic field depending on a ship's position from the magnetic poles. We really just did not know all that we needed to know while trying to develop this weapon. In the winter then of 1924, testing of a prototype exploder on a torpedo will actually commence. And Newport will conduct 2 successful test firings with the developmental magnetic influence exploder using unarmed Mark 10 torpedoes which passed under a target submarine. At that point, Newport desired a live fire test with a decommissioned battleship. But the Bureau of Ordnance denied this request, and they instead obtained the decommissioned submarine L8 to serve as a target. You can see L8 here on your screen. In Narragansett Bay on 8 May 1926, Newport personnel readied a Mark 10 torpedo with a live warhead containing a prototype magnetic influence exploder. Keyword prototype. The first torpedo ran too deep and it passed under the hull without detonation. That is a photograph there on the left. A second torpedo passed just beneath the submarine and it detonated with spectacular results. That's our photograph here on the right. And this sent L8 to the bottom. With this obvious pleasure at a 50% success rate, Newport urged the adoption of the exploder for submarine torpedoes, and Buord ordered the torpedo station to proceed with further development of the device for use on both surface ship and aircraft torpedoes. Now, the physical exploder and the science underpinning it required further bench development. Despite this apparent success of L8 sinking, Newport's research department admitted that all prior development was attempted, quote, with no proper knowledge or no proper foundation in knowledge of the magnetic field to be encountered under ships or of the current that might be induced thereby, end quote. One positive development in 1928 for the prototype came about with the invention by General Electric electrical engineer Albert W. Hull of the Thiatron tube, which is a gas-filled tube with a hot cathode, anode, and a control grid between the two elements. The tube could handle high currents, and it functioned like a controlled rectifier and high-power electrical switch. And you can see a Thiatron powered up there on the left. 2 years later, in 1930, the prototype magnetic influence exploder had advanced significantly enough to warrant greater field testing. To better understand magnetic fields, Newport and Buord arranged in winter of 1930 for studies in southern latitudes with what was now referred to as the, quote, index mechanism. And this was for magnetic induction and exploder, so thus index mechanism. Several examples of this device took part in field tests off Colón, Panama. Additionally, Newport personnel would take approximately 7,000 magnetic readings off Cuba on the magnetic equator, as well as off Rio de Janeiro. All this new information on the magnetic fields moved Newport to further refine the mechanism's electrical system. And armed with the new knowledge and an improved design, Buord felt confident enough to purchase 30 index mechanisms from General Electric in 1931 at a unit cost of $1,012.89. This is about approximately $17,500 today. So now that they had physical production examples in hand, Newport subjected these to increased testing. Their researchers in the winter of 1932 and 1933 sent several of the production models to the Caribbean and South America for testing aboard the destroyer Babbitt. The heavy cruiser Indianapolis also served as the target vessel for 100 test shots along the equator between 10 degrees north and south latitude. Positive test results convinced Newport the magnetic influence detector could work in multiple latitudes. And in the summers of 1932 and 1933, Newport Ordnance Engineer Chester T. Minkler filed patents for a, quote, magnetically controlled torpedo firing mechanism. You can see his patent drawings there on the right. So Newport at this point was supremely confident in the exploder, and they thought the time was ripe for yet another live fire test. Buord really intended for the index mechanism, and this is specifically the magnetic influence element, to be used against heavy warships, really we should say armored warships. And in 1932, the Bureau asked for a heavy cruiser to serve as a target. The following year, Admiral William H. Stanley, who was Chief of Naval Operations, as well as the Bureau of Construction and Repair, instead offered Buord use of the destroyer Erickson for live fire testing, provided that Buord cover the cost to raise and repair the vessel should the live fire test perform as intended. Unsurprisingly, Buord said, we'll pass, we're good, thank you. And instead, the Bureau of Ships subsequently sold the Navy's first ship to fire a torpedo in combat for scrap in 1934. And that same year, the index mechanism was officially designated as the Mark VI exploder. Newport would make one final addition prior to production, and that was adding an anti-countermining device. And this is what became known as the Mark VI Modification 1 exploder mechanism. Production of the Mark VI Mod 1 thus commenced at Newport Torpedo Station. Working in isolation, the station's craftsmen handmade the various components of the device, and these were then assembled into complete exploders by a very select group of personnel in the research department, and then tested to maintain secrecy about the device. To avoid foreign nations learning of its existence and developing countermeasures, we'd think degaussing, and this was albeit at the expense of technical education for the Navy's torpedo men. Newport would also produce a separate exploder. This was designated the Mark V. This had the exact same base plate of the Mark VI, designed to fit into the Mark XIV torpedo's warhead. But the Mark V lacked any of the electrical elements essential for the magnetic influence device. And outside of Newport, only a handful of officials even knew the existence of the Mark VI Mod 1 exploder. Now, in 1938, in anticipation of the day the Mark VI could be revealed to the Navy, Newport published a confidential ordnance pamphlet for the upkeep and operation of the Mark VI Mod 1 exploder. The pamphlet, which you can see the cover here, offered a general description of the mechanism and all the necessary instructions for its care and adjustment. But in a nod to the exploder's assembly process, the pamphlet cautioned, quote, "There are fits between certain parts of the mechanism which militate against complete interchangeability of parts, even though the parts are within drawing tolerances," end quote. So in a nation where we have the firearms industry pioneering interchangeable parts, and the automobile industry developing assembly line production techniques, essentially Newport's Mark VI is more an object of art than an industrial weapon of war, because these are handmade, hand-assembled, hand-fitted, hand-refined mechanisms. Probably a watchmaker or clockmaker would be a good analogy here. Now, within the collections of the Smithsonian Institution's National Museum of American History is an original early production example of the Mark VI Mod 1 exploder, and this is serial number 2086. The museum acquired this device in its original shipping box in 1975 from the National Armed Forces Advisory Board, and they in turn acquired the device in a transfer of miscellaneous ordnance in about 1965 from Naval Ammunition Depot, Hastings, Nebraska, just prior to the depot's closing. Now, within the exploder shipping box is a form listing the device as having been assigned to the Atlantic Fleet destroyer Hillary P. Jones and being inspected and tested aboard the destroyer Tender Prairie on June 9, 1941. Intriguingly, Mark VI Mod 1 Exploder 2086 is a fired example. It was clearly a dud. The voltage regulator tube is missing, the thiatron is very badly damaged, the guide rods for the firing pin are visibly distorted. There is no safety chamber atop the inertia impact exploder body. So exactly what transpired, either in testing or in operational use for this example, to be damaged and preserved, it remains unknown, and I have yet to uncover any document with this serial number besides the form you see before you saying what happened to it. But this will provide us a means to really discuss the components and show how they all interact, as well as you can see the elements of the Mark III and the Mark IV incorporated in the Mark VI. Now here is the Mark VI Mod 1 exploder before you. This entire assembly weighs approximately 90 pounds. This is a very heavy device. The magnetic influence and inertia impact elements are mounted to a very heavy bronze base plate, which you can see there at the bottom. It measures 14.5 inches by 12 inches, and it is substantially greater in size than the Mark III exploder. Now, early in its development, Newport found that the bronze construction made possible the use of a higher voltage in the operating circuit. And the exploder is actually located in the underside of the warhead. It is located 12 inches from the forward nose of the torpedo, and is only designed for the Mark XIV and the Mark XV. Now, installation of the Mark VI inside the torpedo warhead requires 24 separate screws, as well as a rubber gasket and a gasket compound to ensure a watertight seal. So we have over a square foot of surface area here to seal, and the size of the base plate and the overall weight will make removal and remounting of the exploder at sea a very complicated procedure, especially with this potential for leakage. Now, on the underside of the bronze base is a round plate, and that is actually, which I have an arrow there, covering the anti-countermining device. It's essentially a diaphragm, and the idea here is if there's detonations in the water, either from depth charges or other means, this will prevent the device from being triggered and detonating. Now, adjacent to the anti-countermining device is a channel, and this is for seawater to flow through, and interact with an impeller of 15 convex blades. And you can see my cell phone photo there of the impeller. Now, as the torpedo moves through the water, the impeller will spin like a water wheel, and a shaft from the impeller connects to a direct current generator. The impeller, which I'm kind of guesstimating here is probably inspired by the Mark III exploder, can functions for both power generation, but also the safing and arming of the weapon. Now, the generator, developed by General Electric, has a double wound armature with 2 commutators to supply both high and low voltages. And this is to energize the Thiatron, the voltage control diode, a potential divider, and a solenoid. The low voltage, high current power will flow to the Thiatron, and this heats up the cathode element, or the filament, excuse me. The high voltage then will travel to the Thiatron's grid element, the anode plate, and the warmed cathode filament to ensure the correct voltages. And this is particularly the biasing voltage critical to keep the Thiatron from triggering. Now, the opposite end of the shaft from the impeller to the generator will terminate in a worm gear. This will mesh with a gear on the vertical drive shaft, the middle of which has another worm gear to mesh with the delay switch control. The safety device in its closed position essentially acts as a short circuit, and this prevents high voltage electricity from the generator flowing to the Thiatron until the torpedo has traveled about 450 yards from the point of firing, thereby arming the exploder for magnetic influence explosion. And this consists of a worm and a worm wheel, which only partially turns a set distance. Now, during testing, the engineers at Newport learned that a very rapid change in torpedo direction, incidental to launching at high speed or in rough water or a quick gyro turn, this could actually trigger the Thiatron inadvertently and fire the weapon. After the delay switch then opens, the arming screw of the delay device will unlock a firing pawl linked to the solenoid lever system. The Thiatron tube warms up, and then a booster charge of Tetrol will travel upwards from the safety chamber in the booster cavity after the torpedo has traveled 397 yards. This then arms the exploder for impact explosion. So you have magnetic influence as well as impact explosion. For both of these operations, the torpedo will be fully armed once it has traveled about 460 yards in the Mark 14 torpedo at high speed, which is about 46 knots. Now, the main component of the magnetic influence device is mounted on the side of the base plate. To detect and measure the magnetic fields, researchers were essentially using an induction magnetometer. The physical sensor which Newport employed, referred to as the pickup coil, is seen here, and it consists of 100,000 turns of fine copper wire around a thorough magnetic tubular core inserted inside of a 4-inch diameter, 12-inch long can. And through the center of the can, you pass a 34-inch long core rod made of permalloy, which is a nickel iron magnetic alloy known for its property of extremely high magnetic permeability. So the coil and the rod will collectively function in a passive mode to measure the changing magnetic flux intensity levels of the Earth's magnetic field. And as the torpedo is traveling to its target, the pickup coil will produce a very small variable voltage outputs, which are increased by the core rod. And when the assembly is in the proximity of the hull of a ship, and this is between about 5 to 20 feet, the perturbations of the ship's magnetic field produce an electromagnetic field with increased voltage on the assembly. So at this point, there are 2 glass electrical tubes, the Thiatron and the voltage regulator. They're on adjacent sides of the generator. The latter will control the output voltage of the generator regardless of the speed of the impeller, and this will ensure constant regulated voltage necessary for use in multi-speed torpedoes. The Mark 14 really has 3 speeds. Eventually, though, the Mark 14s are really only going to be used at high speed, the 46 knot setting. But the former, the Thiatron will really act as an amplified electronically actuated switch. And this is providing a switching action for when the pickup coil and the core rod sense that change in magnetic fields at increased positive voltage. At a preset value, the increased positive voltage will overcome the negative voltage on the Thiatron's grid. This removes the bias holding back the electrons on the cathode. Those are then going to flow to the solenoid, which is located immediately adjacent to the generator. When that solenoid receives the energy from the activated switch Thiatron, a spring cushion armature will spring upward 1/4 of an inch, activating a pawl, whose attached arm will engage a finger, which on contact pushes upwards. It dislodges the firing ring of the inertia impact exploder mechanism to detonate the warhead. So you have essentially an electrical device actuating a mechanical function. Now, directly atop the generator is the inertia impact exploder. And it's basically an evolution of the Mark III, which did not integrate with the magnetic influence device. The redesigned exploder itself is the Mark IV exploder, which is used in the Mark XIII aircraft torpedo. If you can see the two little red crosses, that's to show the cap that actually will contain the booster charge and the primers. You can see the 4 screws there on top of the Mark XIV. That cap sits above there. Now, while the Mark VI exploder was rugged enough for launching from high-speed aircraft at 100-foot elevations, the sheer weight of that bronze baseplate precluded its use in the Mark XIII aerial torpedo. But like the Mark III, the Mark VI's inertia impact exploder orients its firing pins perpendicular to the orientation of the torpedo's path of travel. This design from the Mark III served faithfully in the Mark 7 through 12 torpedoes, and those operated at speeds ranging from 27 to 46 knots, at weights of 1,588 pounds to 3,505 pounds. Presumably then, if the Mark III could handle the forces of impact at those speeds and weights, presumably a subtle redesign would not affect reliability for the Mark VI's use in the Mark XIV and Mark XV torpedoes, which are weighing about 3,000 to 3,438 pounds while traveling from 32 to 46 knots. It seems pretty reasonable. And like the Mark III, the Mark VI is extremely sensitive to impact. It requires no more than 5.5 pounds of pressure to trigger this mechanism. But in lieu of an inertia ball and the scissors of the Mark III, the new iteration here utilizes an inertia impact ring type assembly. So as the torpedo speeds through the water, the impeller rotates the arming screw, which among other duties compresses the arming screw and firing spring, and it also unlocks the safety balls, firing pin guide, and inertia firing assembly. At the point of impact, when the torpedo is traveling at a top speed of 46 knots, the perpendicular impact force of generation will measure about 500 times the force of gravity. And when the torpedo hits its target, the inertia forces then shift the 8-ounce brass inertia firing ring relative to the rest of the mechanism. You can see my fingers are holding the firing ring. This then transfers energy to the trigger plate above. Essentially, that inertia ring, instead of, we'll say, being on a flat plane, kind of tilts at an angle. This lifts the trigger plate and the trigger cap. The cap then slides upwards 3 millimeters. It releases 2 firing balls into cuts in the cap body. That frees the spring-loaded firing pin guide, carrying these 2 little firing pin points seen there in the upper right. The pin guide then is accelerated by the firing pin spring and thrust upward along dual guide rods until it completes a full stroke. And there, the 2 guide rods are flanking the firing pin body there. At that point, the pin guide will, which is seen on the photograph there on the right, it's the upper part of the firing pin body with the 2 little prickers there. That will terminate at the underside of the safety chamber cap, seen on the left, holding the booster cap, which is in the very center of that. And those 2 little pins will impinge on 2 small primers. Those have a detonating charge. Those will set off a detonating charge of 65 grains fulminated mercury. The released energy from those 2 primers will ignite half a grain of gun cotton. That detonates the 8 ounces of Tetrol in the booster charge, and then the warhead's TNT, later Torpex, explosive. All of these complicated tasks are designed to occur in a fraction of a second, ideally. Suffice to say, the Mark VI Mod 1's exploder complexity and its limited exposure is where we all need to pause and wonder, will it work? Vice Admiral Charles Lockwood, the commander of Submarine Force Pacific Fleet, referred to this exploder as a, quote, Rube Goldberg device, with good cause. As any number of these complex mechanical or electrical systems, if properly manufactured, assembled, or serviced, could fail, it would basically transform over 3,000 pounds of Mark XIV or Mark XV torpedo into effectively an underwater shopping cart to scratch and dent the hulls of enemy vessels. To their credit, Newport and Buord made many efforts to better understand the Earth's magnetic fields and tune that magnetic influence device to operate consistently in ideal conditions with test warheads. But there's a hard reality here. The finished exploder had never been used in a live fire test. The finished one never was used. It was a prototype. The magnetic detection device, which was incorporated on an early prototype exploder prior to that added refinement of the Thiatron tube, even then only had a 50% success rate against a target submarine, rather than the really intended targets of a battleship or heavy cruiser. Meanwhile, the inertia impact device, the evolutionary element, carried the totality of design lineage of American torpedo exploders. Meticulous machining, detailed design. It produces this incredible, intricate ballet of screws, gears, and springs to ensure that the torpedo would not detonate until a safe distance from the point of release. When activated, the various parts all work collectively to move a pair of firing pins on a guide in a linear motion to convert mechanical into chemical energy to detonate the warhead. The Mark III, which formed the foundation for the Mark VI's inertia impact device, had no known torpedo detonations against enemy vessels. How the Mark VI inertia impact exploder would perform when paired with the new Mark XIV and Mark XV torpedoes remained unknown. And the U.S. Navy's submarine and surface forces went into battle in World War II with unproven torpedoes whose detonation depended on under-tested exploders. Suffice to say, the laboratory of war would soon yield disturbing data. On that cheery note, I thank you all for your time and attention. My contact information is there at the bottom, and I look forward to answering any questions that you all may have. Let me now stop sharing, and back over to you, sir.
Makes the head spin, Frank.
Mine too.
And so eventually the whole concept of a magnetic influence igniter went by the wayside. Just too many moving parts, too many things to potentially go wrong. Was there ever a successful? I mean, the horror stories of submarines scoring any number of hits that just went bonk at the beginning of World War II. Those stories, especially in the Pacific theater, are legion, where we go out and come back with zero success because the torpedoes simply didn't ignite.
Absolutely. There's a handful of examples. It's difficult to say, was it the impact exploder or the magnetic influence exploder that resulted in the destruction of an enemy ship and or just the detonation of the torpedo. I like to refer to this as the wonder weapon. I wonder if it will work. And even that was a problem that the Germans, when they entered the Second World War, they had a magnetic influence exploder, which worked great in their testing areas up there in the Baltic. Once they took it out of the Baltic, it just didn't work. And they had all sorts of problems with their magnetic exploders, which they eventually got rid of. The British ran into the same situation. They got rid of them. Essentially, we simply did not realize that the magnetic fields on the Earth are very complicated and very widely. Plus, the Japanese did have degaussing of some of their warships. And so the Navy discovered by late 42 into 43, if you degauss your warship and you over degauss your warship, they just don't, these exploders completely do not work. But the challenge here, and this is kind of a talk which doesn't go into the problems, and that's sort of done intentionally.
Right.
But one of the things that they discovered is that impact exploder itself didn't work. And for the audience out there, COVID made it very difficult to write this paper because I just couldn't get access to the primary records. More recently, within the past 2-3 days, I was at College Park, Maryland at the National Archives, as well as the Navy Department Library in Washington. And one of the more fascinating things that was recognized in about September, October of 43 during live fire testing in Solomon Island, Maryland, is that the exploder only sits about a foot from the nose of the warhead. And that torpedo traveling at 46 knots, 3,000 pounds at 46 knots, when it hit the side of a vessel, it was compressing so fast that that compression broke the exploder mechanism before it could function. And so in many cases, they would pull up the torpedoes, the warhead's completely smushed in, even concrete or Torpex or whatever, and the exploder is mangled. And even though it was designed for all these complicated actions to happen in a fraction of a second, that was still not enough to overcome the law of physics. And so this is a situation that the Navy realizes they need to strengthen many of the components of the Mark VI just to withstand that initial impact shock. But again, with the Mark III, they said, well, same speeds, same weights of torpedoes, relatively. Why would it not work? But even there, too, limited testing. We simply didn't know. And it's a good case study of when we're thinking of the complexity of weapons technology, particularly naval technologies, and all the efforts of the crew of a boat to get it in a firing position and get that weapon on target, the simplest thing, right? The 50-cent washer, the 10-cent screw, whatever. If it fails, something as complicated as the Mark VI. That's why I call it, 3,000-pound shopping cart. It's going to dent the side of your car and give you a headache, but it's just not going to destroy your target. And for the first 21 months of the war, we're not able to sink enemy vessels. If we had been able to destroy not just the Japanese merchant fleet, but some very valuable Imperial Japanese Navy warships, would we have needed the atomic bombs? Would we have needed the massive 20th Air Force bomber offensive in Japan if the Navy had been able to really decimate the Japanese shipping in the first 2 years of the war? And that's one of those big what ifs.
So that begs one of the questions, because we read about, especially in the War in Atlantic, both during World War II and World War I, where the U-boats seem to have had some success with use of torpedoes. How different was their design from what we were trying to do? Or do you have any insights on that? I know that's a little bit outside your...
No. In that case, again, we're just using contact exploders. Okay. The challenge there would be, particularly if we say from the German perspective, the Germans are using deck guns very effectively. So there are many situations where some of the highest scoring aces are very successful with their deck guns. The boats are operating in a surface capability. They're only submerging for the certain periods of protection, right? We have ASDIC, but we don't have radar yet. Right. So they have a lot more flexibility, but they're using impact exploders. And a lot of the vessels then, either the damage control techniques, the design techniques, particularly merchant vessels, many are able to limp back home, but the impact exploders are basic but effective. Right. They're very cut and dry in their design, but they're not necessarily going to be effective against armored warships or warships that are designed to withstand damage and come home. Hence this idea of, well, what if we can develop a more effective weapon to get around torpedo defenses? It's in want of a theory, so to speak. And so thus we see what the Japanese will do. Let's take it forward. The Japanese, when they design what we historian Samuel L. Morrison calls the long lance torpedo, the Japanese look at the magnetic influence technology and go, nope, it's not going to work. Their solution, put a bigger warhead. They just pack a lot more bang for the buck in their torpedoes. So they're using TNT, but they're using much larger quantities of it. So when one of their long lances, oxygen-powered torpedoes hits a ship, it's just sheer blast potential with that impact exploder blasting hole, which basically we will follow in late 43 into 44, 45. Why? Because Torpex, and particularly the development of RDX, or Research Department Explosive. So you can cram, the sun is like 150 times greater explosive capability compared to TNT in the same size warhead. So what we're doing then is we still have a big warhead on the Mark 14, the Mark 15, but it's a much more powerful explosive. So it's going to achieve a similar effect of damage that the Japanese are achieving with their torpedoes. So, and the magnetic influence, the Navy will eventually do I think it's a Mark 6 Mod 10 and a Mark 6 Mod 12, well into the late 40s, 50s, 60s, because we had that many Mark 14 torpedoes in reserve. But that magnetic element is completely eliminated. They actually keep the pickup coil there solely for trim purposes. They have like a weight equivalent there for trim purposes. So it looks like it has it, but it's basically an impact exploder. And I can't speak to modern torpedoes because most of that stuff's classified, but magnetic influence is still one of these aspects that it's just never really, most navies have really avoided it. And why? Because we now have wire guided torpedoes. So there's to achieve the same effect, there's different means to aim, target, and detonate the weapons.
We have a question from one of our listeners. It is difficult to imagine the danger of being tasked with retrieving a failed torpedo with a Mark 6 Mod 1 exploder. Takes me back to my off the coast of Vietnam days recovering exercise missiles. Did they recover many of them to learn the root cause of why they failed?
there's a very famous incident, and I know Admiral Lockwood has written about this. In fact, I tell you, ma'am, sir, who wrote the question, I'd be happy to email you the letter. In fact, I found at the National Archives where Admiral Lockwood talks about this, along with Swede Momsen. They went down in, I think it was Mark V hard hat dive suits, because they fired the submarine Tenosa, fired something like 15 torpedoes at a Japanese whaler. 12 were duds. And the captain of Tenosa decided, that's it, I'm going to bring my last 2 fish home. He brought his last 2 fish back to Pearl. And Admiral Lockwood said, okay, I've had enough of this. And they will fire these at some underwater cliffs there in Hawaii. First one detonates. Okay, seems to work. But the second one's a dud. And Admiral Lockwood and I think it was Captain Momsen at the time go down in dive suits. And it was actually 3 skin divers from Hawaii. And it was a young man, it was like 15, free dove with no respiratory, no breathing apparatus, free dove 50 to 60 feet and hooked a rope around the tail of the dud torpedo. And they actually pulled the thing up. The warhead was all, smushed in. The exploder was mangled, but they were able to get that safing cap off the top, and they could see that the firing pin, that the little prickers did not hit those primers with sufficient force to detonate it. And that's when they figured, aha, now we have an idea why it's not working. And from that, I know there's a movie of John Wayne that depicts this. Lockwood grabbed a bunch of warheads. They melted out the TNT because it melts at like 180 degrees Fahrenheit. You can actually melt the explosive out, and they filled them with concrete and they dropped them from a cherry picker. And they realized if you drop them from like 100 feet, you actually achieve about the equivalent of 46 knots when it hits. And again, they were mangling the exploders, but that's when they realized the firing pin. The solution was take that whole firing pin body, thin it down, cut the mass of it, and put a much stronger spring on it. And that would actually allow you to enough force to go bang and hit those primers sufficiently to detonate it. They did other variations of that. Those 2 little guide rods, which distorted, and you can see that on the model we have at the Smithsonian. Again, from the sheer impact, they made the pins a lot stronger. The base plate, as heavy as that darn thing is, that was too weak to withstand that impact shot. So they had to strengthen that too. Again, we think about this, and maybe a good analogy is automobiles, right? You think, everyone says, don't buy the first generation of car, because all those little design faults that hadn't come out in all the testing will begin to manifest themselves in the first years of ownership. And so car, oh, sorry, I'm rambling, and anyone knows me.
Fine, because that leads right into the question.
The next question
you mentioned that, the cars and improvements almost every year. Actually, John asked, why did it take so long? We're talking about over 2 decades. We're tinkering with variations on a mechanism. Was it we just weren't spending the money to test the weapons?
Money was a big problem. They didn't. A torpedo is about a $10,000 weapon in the 30s. The exploder alone is what, $1,000 to that. And we know if you test exploders against a hard object, they're kind of destroyed. You just blown that money in testing. They didn't want to spend the money. Let's take this another way. Perhaps we could say they didn't understand enough about the science of testing. It's one thing to test it on a bench. It's another to create a test that simulates combat conditions, that simulates the environmental conditions. Lockwood essentially did that. He did several very practical tests. One was with the depth regulator on the Mark 14 itself. That's a different story. But Lockwood came away to test this and say, determine this is your fault. The problem with the Mark 6, all these faults would layer upon each other, and it's difficult to figure out what. But again, Lockwood figured out a practical way to test it, but it still was destructive in mechanism. It was still expensive. The upshot is we're in a war, buy war bonds, buy more exploders, buy more warheads, we can destroy more stuff. But that's one of the big problems. Also, secrecy. All the knowledge, all the wisdom of this is at a wonderfully named place called Goat Island, and all the knowledge is contained at Goat Island. The manuals for the exploder, and the one you saw there was I scanned at the National Archives. I'm happy to send a PDF of it if anyone would like it. Those documents were locked up in ship safes. The exploders themselves were locked up. The Navy even issued a dummy, the Mark V, which had the same, in theory, trim characteristics of the Mark VI, but it had none of that electrical mechanism. So how, if we think about it, in the summer of 41, the Navy finally said, okay, we're going to issue these to the fleet. We're going to send these out to the Atlantic, Pacific Fleet, Asiatic Fleet. But they had been under lock and key. I think the Pacific Fleet had one petty officer qualified to repair them. And I can say this much, the manual between 1938 and 1942 is a night and day difference. The 42 manual is chock full of all the data that the 38 manual does not include. The 38 manual doesn't provide adequate drawings, schematics, if you have to maintain it. Or, again, it's very little information is sent out about it. So even from that perspective of maintaining it, loading it, testing it, you're very much at a loss. Why then does it take Navy leadership to recognize the problems? To some extent, it's the Mark 14 is a flawed torpedo. We could say that really the weapons carrier, if the warhead is really the weapon, the carrier of it is a flawed device, and its faults are hiding the faults of the exploder. In this case, they're running too deep. So the magnetic influencer might have been working perfectly. But if it's too deep, even if it detonates, it's not going to accomplish its feat. In other cases, we know they were working because they were detonating prematurely. So we know that the magnetic influencer worked. And from a periscope or from your sonar man, you might hear the explosion. You can look through the periscope. You see the big water plume. You think the ship is hit, but in reality, it's maybe detonating 10 feet, 15 feet, 20 feet, 50 feet from the target because it's detecting the horizontal magnetic field from the ship's hull. So in that case, the technology works, but it's our limitation of the science of the Earth's magnetic field that we're able to really come away from this knowing how it succeeds. Plus, let's be honest, it's the Bureau system. Ordnance is saying, it's not our fault, it's perfect. You guys are the problem. Blame the petty officers, blame the submarine commanders, blame everybody. It's not us. So business as usual, perhaps, depending on where you work. But it was easy to point fingers at the operators, saying it's user error. It's not designer error. And one could attest that to the limitations when you have a monopoly and this brain trust of knowledge that they're not willing to listen or be willing to admit fault. And unfortunately, that costs a lot of lives and a lot of money and a lot of wasted time in a war that we want to get this thing over sooner rather than later.
Right. Thank you for that.
Very long answer. Sorry.
Top of the hour. I hate to cut you off. I could listen to you all night. And then, your comments, I think about the development of the most recent warships, the timeline compared to the timeline for previous generations of war ships. That's mind-boggling. And the output you were talking about, for one of a screw, I'm thinking of that, high energy railgun that is, a long highway to nowhere, it seems.
Or what GPS guided rocket propelled artillery shells that are $1 million a shot. We think a torpedo is expensive.
A lot of those.
Yeah, we thought a torpedo is expensive.
Well, Frank, thank you for another fascinating lecture. We will have you back again, and so be careful what you offer because we're going to take you up on it. I want to thank the audience for listening and remind everybody that within the next few days, this will be available as a YouTube presentation on our Commandery's past events page. I want to wrap up by letting everybody know that our next talk will be on the 29th of October, same bat time, same bat channel, 29 October at 1900 Eastern, still daylight time for one more week at that point. And we will have Dr. Bill Thiessen to share some Coast Guard history with us. So we look forward to that. And again, Frank, I want to thank you for the program this evening and thank our attendees for joining us this evening. And one of our attendees was a former sailor aboard the USS Mumson, DG 92. And so this certainly rang near and dear. Want to thank everybody. And with that, I wish you all a good rest of the day, rest of the evening, rest of the night. And see you next month. Bye-bye.